Okay, so we're going to take a little look at polar symmetry for a few minutes. I'm going to mainly work on the easier questions, and I will dabble in the more complicated questions at the end of this. I don't want to get too bogged down in that, but there are some problems get a little bit tricky on this one. So one thing that's important, and these are our base arguments that we are going to be using in this idea, is that when we are checking to see if things have symmetry, these are some of our underlying stories that we're going to utilize. One is that the cosine, and incidentally, the secant is also one of those, is an even function where replacing x with negative x has no relevance on the problem. That's going to help us a little bit. And replacing x with negative x actually does make a difference in this particular story when you have an odd function like a sine. Now, that's one of the pieces. Now, the second piece here that I should put down here, and I'm going to slide this up so we have this information as well as our various tests. So the first test is for x-axis, and it turns out because polar coordinates have an infinite number of representations, it's a little complicated because what we're wanting to do is something like this. I'm wanting to replace r and theta with, for example, r and negative theta, because as a picture, that means this coordinate right here should be exactly the same as this one that's right here below it. And if that's true for every r and every theta, that the negative r with that theta is the same, then it would demonstrate that it has that x-axis symmetry. But it turns out because there are an infinite number of representations, I could also get there by doing the following. Now that feels a little awkward, but understand if I went to pi, take away theta, that would be up here. But then if I went backwards, I'd be in that same location. Now, please understand, sometimes that's going to be a necessary thing. Now, this is the nicest formula to use. This is a little harder to use, but there's good reasons for it. And we'll see that as time goes along. Checking for y-axis symmetry is, again, pictorially saying that I've got something over here and I've got something over here. So again, r and theta is over here. Well, this would be pi take away theta. So I could replace r with r, and I could replace theta with pi minus theta. So our first test is to say r and theta goes with r, so r becomes r and theta becomes pi minus theta. But as it turns out, you could have also rotated down into this by making theta negative, and then going backwards, r would land in the same place. And last but not least, the origin symmetry, also known as pole symmetry, has to do with the idea that you have r and theta up here and you have this guy down here. Now, keep in mind, these are exactly pi units apart. So I could replace r and theta with r and pi plus theta. I could just add pi to them. And I should get exactly the same thing because rotating 180 degrees, also known as pi radians, should be the same thing. Or what I could do is just go ahead and turn to theta, just go backwards r, and that would be the same thing. So in each case, we have two formulas that we can interchangeably use. And you'll notice that this one looks easy. This one right here, negative r and negative theta looks easy. Negative r and positive theta, that looks easy. Those are the easy ones to use. And so those are the ones that I start with. And I only go to the other ones if they fail. Because what you will notice as we go through these in every single situation, you should already know the symmetries because we've studied the graphs. We know what they kind of look like. We know that things are going to either have one symmetry or they're going to have all three, but they'll never have two. And that's an important little feature. You can have one of these symmetries, all three of them, or that's it. One or all three, there's no other options, okay? So let's go ahead and take a look at a couple of examples that I think you'll find to be fairly simple. So let's take a look at r equals, let's say, something like 12 cosines of 8 theta. Now, right off the bat, the first and easiest way to demonstrate that this is actually has all of the symmetries is that if we go ahead and replace our theta with our negative theta, let's see what happens. That's our x-axis symmetry test. So I'm going to replace r with r. I'm going to replace theta with negative theta. But because of the fact that the cosine is even, I can pull that negative out and throw it away. And I have this statement right here. So you'll notice that it came right back to where the problem started. And so we're good to go. And so x-axis symmetry, I'm just going to say check. I have that. Now remember, it's either going to have one of those symmetries or it's going to have all three of those symmetries. Now, the origin one is the tricky one. And this is actually tricky on all of those. I was actually thinking I would do this one a little bit later, and I guess I just jumped the gun a little bit. But we could test either one of those that we want to do. And so what I want to do is I'd like to go ahead and look at origin, although y-axis has the same level of difficulty. And so I always say I'd like to start with the easy one first. And I want to replace r with negative r and theta with theta. But see, again, I know because this is a rows with an even number, I know it has all three. So I know that's what's going to happen. But see, if I replace everybody r with negative r and theta with theta, I would end up with r equals this. Well, that is not the same as the original problem. And so it appears that it fails that test, but I know better. I know that it actually has that. So this is one of those situations where I like to call that a false negative story. And I'll try to show you really quickly in Desmos why that's actually true. So let's go ahead and take a look at this. If it fails, it should produce something that is totally different. So we'll take a look at a Desmos graph of what r equals 12 cosine 8 theta looks like. Okay. All right, 12 cosine 8 theta. Now you can see that it does have, in fact, all of those symmetries. But the thing that I wanted you to see is that if I took this graph right here, and I replaced this r over here with a negative r, did it actually change what the graph looked like? So that r and negative r look like they might be different when in fact they are the same. But how would you know that they're the same? Because they don't look the same. We have to go with one of our secondary stories. So here's what we're going to do. We're going to go ahead and tangle with this one right here. We had two ways. Let me go ahead and stop that share and go back to my document camera. We're going to go ahead and try the other option where we replace r and theta. So this becomes like, I know it should work, but it didn't, right? And so I'm going to replace r and theta with r and theta plus pi. Okay. Now this is going to be kind of interesting. So I'm going to replace r with r. I'm going to replace theta with theta plus pi. Now, this is going to look terrible for a few moments, but hopefully you're going to catch that it actually comes out pretty nice in just a few moments. So I want to remind you of some of the building block equations that I had. This is the cosine of something plus something, isn't it? So I have 12, and now I have the cosine of alpha, which is 8 theta, cosine of beta, which is 8 pi, plus the sine and the sine. Now, I told you I really like you to write the formula down, and in fact, I probably should write that up here. Cosine of alpha plus beta was cosine of the first, cosine of the second minus sine of the first, sine of the second. That was our formula that I just utilized. But the nice thing is 8 pi is really all the way around the circle several times, pointing right over here at the coordinate 1, 0. And because of that, I know that the cosine of 8 pi is in fact the number 1, and the sine of 8 pi is 0. And so all told, what I end up with is r equals 12. I get the cosine of 8 theta times 1 plus sine of 8 theta times 0, which means it's gone. And so this is all that I have left, which is actually the original problem. So interestingly enough, it then passed the origin test. And as we discussed in class, you can never have two symmetries. You either have one of them or you have all three. And so because this has two of those symmetries, I know the third is, again, automatic. So that's a good example of how that plays out. Now, let's go ahead and take a look at, because that's one of the things that people wanted to know, what about the failure? What about that failure story? So let's take a look at one that I know is going to have some kind of a failure, okay? So let's say we had 10 minus 5 sine theta. Now, one thing that I know for a fact is that this should be a limicon. It should be extended down like 15 units. 10 plus 5 is 15. 10 minus 5. It's going to be this kind of shape. And I should know that it's almost like a messed up circle, but it's going to be extended more down than up, right? Which means I know it's going to have y-axis symmetry, but not x-axis symmetry. Okay, so here we go. And I know it's going to fail origin too. So let's see what happens. So let's start with the good stuff, y-axis. Now, as it turns out for this problem, I have enough experience to know that trying the simple test by replacing r with negative r and theta with negative theta is not going to do it. Because if we do that, it's odd, I can pull that negative out. All of a sudden, I end up with something that doesn't really truly look like the original problem. In fact, it's very similar to the original problem, but not identical. So that's like, but I know it should. That's why I said this is complicated. So what I'm going to do is I'm going to try the alternative one that is the slightly harder one. I'm going to replace r and theta with r and pi minus theta. So that's where we go. So I'm going to replace r with r. I'm going to replace sine of theta with pi minus theta. Now again, whenever you have the sine of the difference of two angles, it's the sine of the first cosine of the second minus cosine of the first sine of the second. So that's going to be the sine of the first cosine of the second minus cosine of the first sine of the second. And hopefully, by doing some quick math, we're going to get the right things. But the cool thing is that the sine of pi is always 0, and the cosine of pi is always -1. And so putting that all together, I got 10 minus 5. This all became 0, and there's a double negative. It's minus -1, so it's plus 1 sine theta. Well, if you just distribute, this is where we are. And we got back to the original problem. And that proves that, in fact, it does have the y-axis symmetry that I knew it should have. It just gave me a false story right here that looked like it was a no, when in reality it was a yes. Okay, now, x-axis, though, is easier to test. Because if you replace r theta with r comma negative theta, which is one of our nice little x-axis symmetry tests. I'm going to replace r with r and theta with negative theta. The fact that the sine is an odd function allows me to pull that negative to the front, and I get this. Now, this is not a case of a false negative. It looks wrong because it is wrong. You should know that if this is the curve, it's a sine wave, but it would go up 15 and down 5. You notice it's not the same as the original. It's totally flipped over. So this is a no, and it's like a really honest no, because it's not like I think it might be different. We know that it's not the same as the original. And so that's kind of the way we play with this idea of polar symmetry. Okay. And so I did one rose and one limicon, and we did some other ones in class. Hopefully that was helpful. Please let me know if you would be benefited by having some more explanation on that, and I'll see you guys back in class. All right, bye-bye now.